Okay, so we just looked at spring potential energies and how to derive them. We saw using a force position graph and finding the area underneath it. That took some work. We could equate that work to an energy. That's a spring energy here. We see our equation US equals 1/2 kx squared. What we're going to do here is we're going to use this kind of in more of a problem. These are the 9-C4 questions of our unit. And this is where we have some spring that is being compressed or stretched out by some amount, and we'd like to figure out how much energy we've stored in that spring. So we're just going to do number 1 of the 9C4 problems. What we have here is that, and we get to draw a little picture. I'm a poor drawer. This is a pogo stick. Spring. We have a pogo stick here, and the pogo stick is compressed downward by 0.24 meters. So that's a delta x. That's a compression there. So boom, you go down on the pogo stick, and the kid who's riding this, let's make our kid blue. I'm blue, and you can't see the kid behind the pogo stick, but you can see his legs and you see his arms. Poorly drawn by yours truly. Our kid here has a weight of 590 newtons. Okay, so that's the force pushing down on this pogo stick. Remember, that's a weight, that's a force. And we know it displaces by 0.24 meters. What we'd like to do in this problem are two things. The first thing we'd like to do is, what is the spring constant for this pogo stick? What is K? The second thing we'd like to do is, once we find K, what is the spring potential energy, often sometimes called an elastic potential energy, when it's compressed by a different value? So what is that spring potential there? Okay, so what do we have going on for this problem? Well, to solve part A, we know previously that we have a spring equation, F equals Kx. That was from our F equals ma unit. A spring force is equal to Kx. And in our case here, we actually have both F and X. So we can solve the spring force, or the spring constant rather. If we rearrange that equation right here and solving for K, we can say that K equals F over X. And if we wanted to sub in some values here, we know F is 590 newtons divided by X, which is 0.24 meters. At this point, you start looking around. Found the trusty calc! We do 590 divided by 0.24. I know the number's got to be bigger. I'm dividing by a decimal. So when we get a spring constant of 2,458 newtons per meter, we're not surprised here. And that makes sense. We're taking about 600, essentially multiplying it by about 4. That's dividing by 1/4. We get a value that's about 2,400. Okay, so that makes sense for our spring constant. That spring constant here, this 2,458 newtons per meter, that value is never going to change. Remember, a spring constant is intrinsic to the spring itself. It doesn't matter how far you stretch or compress it, it's just a property of the spring. The spring constant exists after that spring has been created. It is dependent on the material the spring has been made out of. Has it been made out of like a flimsy rubber, a very high stress tensile titanium, and the thickness of that metal or object? How many wraps does that object have? What's the diameter of those wraps of the object? So the spring constant, it's a property of the physical properties there of our spring. It's a constant. It's never going to change when we use it for other values. So whenever we go down to part B here, in order to solve for our elastic potential energy or our spring potential here, we know this is going to be 1/2 kx squared. And in the second part of the problem, we'd like to know the spring or the elastic potential energy when the spring is only compressed 0.12 meters. How does that change up our spring potential energies? So whenever we go to actually plug everything in here, what we're going to have is 1/2, and then we just need to drop in this value of K. We don't need to resolve it. That's one of the biggest errors I see. People try to resolve this value. You don't have to. When we drop in this number, it is a constant of the spring. Nothing to change about it. Then we just need to bump up our 0.12 meters. Okay? Don't forget the square. We know we need joules out of this, or Newton meters. So one of these meters is going to cancel out with one of the meters squared, and we're going to get Newton meters at the end of this. So after we dump in all of our numbers, we start running the calculations. I like to do the squares first just because my paranoia sets in. So 0.12 squared, I know that's going to give me a 144 somewhere. The decimal points, multiplying them together, is making that number smaller. So we're going to get 1/2 times 2458 times 0.0144. These are Newton meters, meters squared. We know when they multiply, though, everything will equal out. But we multiply that 0.0144 times 2458, divide that sucker by 2, and we get here that there's a spring or an elastic potential energy of about 17.7 joules. Okay? Now, that's where our problem ends here. But let's think about something further here, kind of a little exercise of the mind. If I compressed this pogo stick back all the way to the 0.24, I doubled the compression, because up here that compression was 0.12 to get our value, our answer. What if I doubled that compression? How would it change our spring potential energy? A lot of people like to answer here that it would double. It doesn't. Instead, it quadruples. And how does that happen here? Well, if we take a look at the equation itself, we see there's a square term here. So what actually happens is when you double the original value, this 0.12, you're actually taking 2 times that original value and squaring it. So you don't just get 2 times the change, you get 4 times the change. If we were to triple the compression, we made it from 0.12 to 0.36. It wouldn't give us a times 4 change here. It would give us a times 9 change. We'd have 9 times as much spring potential energy, because that is 3 times as much, and we need to square that value. So we're doing that twice. We're doing 3 times 3, which gives us a value of 9 there. If we went even further with this, as you can probably see a pattern going, if this was 0.48, you know, if you just follow your perfect squares, we're going to get 16 times as much potential energy out of this spring by doing that. So it's an important thing to keep in mind. If you have kind of numbers that, you know, are multiples of each other, you can just square that double or triple or 4 times as much to get your new spring potential energy. So that's a cool little trick there. But all in all, nothing too crazy of this problem. We're looking at spring or elastic potential energies using the equation 1/2 kx squared, and we found spring constants just using F equals kx. So with that, this problem's finished.